Abstract algebra is a branch of mathematics that studies the properties and patterns with algebraic structures like groups, rings, fields, etc., rather than focusing on traditional numerical calculations. In algebraic structures, sets we define operations that follow specific rules and patterns. These structures are abstract because the elements within them aren't strictly numbers. For examples like groups, rings, fields, vector spaces, and modules. In mathematical abstraction, the process of identifying common properties or patterns across different mathematical systems, then creating generalized frameworks to study them. In historical context of early 19th century, it is need to solve higher degree polynomial equations drove exploration of new areas of algebra. Everest Galois pioneered the concept of groups to address these equations. Carl Friedrich Gauss developed modular arithmetic, which shares properties with groups. New non-Euclidean geometries emerged, and groups help in analyzing them. In evolution of abstract algebra, the power of groups as a unifying tool lead to the development of more abstract structures like rings, fields, etc. Careful refinement of definition ensured these structures were both broadly applicable and insightful. So that, or what are the significance of abstract algebra? As we know that abstract algebra provides the underlying principles and structures used in many areas of advanced mathematics. Abstract algebra now has applications across physics, chemistry, and computer science. The usefulness of abstract algebra continues to grow with new applications being discovered regularly. Remember that abstract algebra is called or also called modern algebra or simply algebra in advanced mathematics context. To study abstract algebra, one needs first a solid foundation in traditional algebra. Second, experience with mathematical proofs. And the third one, capacity for abstract thinking. The foundation of Euclidean geometry. Euclid's Element is a famous geometry book written by the ancient Greek mathematician Euclid. It laid the groundwork for what we now call Euclidean geometry. It's a system of geometry based on axioms and postulates. Axioms and common notions. The terms common notions and postulates are interchangeable in this context. They are basically fundamental assumptions or accepted truths that form the basis of Euclidean geometry. These are considered self-evident and are not proven within the system itself. There are 5 common notions which are essentially rules of logic. First, things that are equal to the same thing are equal to each other. If A is equals to B and B is equals to C, then A is equals to C. Second, if equals are added to equals, the wholes are equal. If A is equals to B and C is equals to D, then A plus C is equals to B plus D. Third, if equals are subtracted from equals, the remainders are equal. If A is equals to B and CD, then AC is equals to B minus D. Fourth, things which coincide with one another equal one another. Imagine 2 shapes perfectly overlapping each other. They must be the same shape. Fifth, the whole is greater than part. This one is pretty straightforward. There are 5 postulates as well, and these are more specific to the concepts of points, lines, and circles. First, to draw a straight line from any point to any other point. This means you can imagine a straight roller connecting any 2 points. Second, to produce a finite straight line continuously in a straight line. Imagine extending a line segment indefinitely in both directions. Third, to describe a circle with any center and radius. You can use compass to draw a circle with any size as long as you have a fixed point as the center. Fourth, that all right angles are equal to one another. A right angle is a 90-degree angle, like a corner. The fifth one is that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which are the angles less than two straight angles, or the two right angles. This last postulate is also sometimes referred as the parallel postulate. These common notions and postulates are the building blocks of Euclidean geometry. By accepting this as true, mathematicians were then able to prove other geometric systems based on them.